So now we're going to look at moments. So we'll have a point Q. Q. And this will be some fulcrum that doesn't move, but we're going to have rotation about it. Okay. We're going to cause that rotation by having a force applied at P. So we'll draw P here. And so we'll have a force applied, say, here. Okay, so consider the force acting on a rigid body. So the red bit there is actually rigid now that we're looking at it. So the red arrow is kind of rotating around. But we apply a force at P given by the well, where is P? It's at a certain displacement from the fulcrum, and we want to hear this thing from the fulcrum to the force. So the force is applied at a point, and the displacement is from the fulcrum. So we could write down something like D is the displacement of P from Q. Something like that. Okay. So the moment then it can be defined. Now we kind of argued this. We won't go through. I don't think we'll go through all of it. But essentially, the bit of the force that does any bit of turning, this parallel bit can't do anything. It's the perpendicular bit that does the turning, and so this does get reduced to what you might know that the moment of a force is the distance, which is the magnitude of the displacement, times the magnitude of the perpendicular force. Now this is a bit funny because a moment is actually a vector because it has a direction. Basically, there's a difference in clockwise and anti-clockwise. So we should write that this is a vector, but then you get an issue because the left-hand side is a vector and the right-hand side is a number. So in fact, this is the magnitude of the moment. So when you calculate a moment, normally, say if you just do distance by perpendicular force or whatever, you're calculating the magnitude of the moment, you're not finding the direction. So what we've been working with now, we've got the M symbol. I'm going to use this symbol, tau. That's a Greek letter tau. It is a vector. And going through what we looked at in last week, it should be the cross product of the displacement and the force. It'll give you the right magnitude. So the magnitude of tau will be the magnitude of the distance, the magnitude of the force, times the sine of the angle in between. And that does give you the same thing as this. And then the direction is given by the, right-hand rule, isn't it? Right-hand rule, which is basically a fancy word for saying righty-tighty, lefty-loosey. So the direction of the moment is given by the right-hand rule, and the magnitude of the moment is the distance by the magnitude of the perpendicular force, which you can show is magnitude of force sine of theta. We would have done that previously. Yeah. Okay. So that's it. If you want to find the magnitude of the torque, you've got two options. You find the torque or the moment, and then you find the magnitude of that vector. Or alternatively, you find the angle between the two vectors. So you can say if you've got, say you want to find the angle between the displacement and the force, you could use the fact that the displacement dotted with the force, which is easy to calculate, is the magnitude of the displacement times the magnitude of the force times the cos of the angle in between. So what that means is, therefore, you can find, with a bit of work, the angle between the two vectors of displacement and force. And then you can use this formula. But usually I'm gonna actually ask you for the full vector anyway. Okay, so let's do some examples. So consider a wrench and bolt subject to a force F, the plan of which is shown here. Okay. Find the moment of this force. So we have this force here. It is now in terms of the bracket. So it's -9 along the X, 9 along the Y, and 12 along the Z. It's acting at 12, 10, 2. About the point A, which is 2, 2, 6. Okay. Assume the distance is measured in centimeters and the force newtons. Okay. So where's the displacement vector here? Displacement goes from the pivot or the fulcrum to the point where the force acts. So displacement goes from A to B. So displacement is equal to the vector from A to B. Now this one, it does ask for the magnitude. So you don't actually have to calculate the full vector product if you don't want to. Oh no, you do. Sorry, it says it right there. Find the moment. Sorry, my bad. So the moment is given by the vector product, the cross product, the moment of the force. Now, okay, we can make a comment. In the previous lecture, we were working with the moment, the work done by a force. And we said that the work done was equal to the dot product of distance and force. Now, if I ask you for the formula for work, you'd probably give me force by distance, and maybe now I'll tell you, yeah, but it's a dot product now. So you got distance dot force versus force dot distance. And if you kind of have a little play around, you'll notice that these are actually the same. So the fancy word here is that the scalar product is commutative, which means that the order of the multiplication doesn't matter. That's not the case for the vector product. So if you look at, say, displacement cross force versus force cross displacement, they're not equal, they're not the same thing, and the relationship between them is that you get a change in sign. Now, what that means is we define it as it's d by f in that order, and the way I do it is I do the work as d dot f as well. So they're both of them are d by f. One of them, the order doesn't matter, but we kind of pretend it does because they're both d by f. And then work, which is a scalar quantity, not a vector. So work is a scalar. It gets a scalar product. And torque or moment is a vector, so it gets the vector or cross product. But they're both d by f, okay? But you should, now a lot of my day students mess them up. You shouldn't mess them up in an open book exam, I'll tell you that much. Okay, so we have to do all this. So it'll be easy enough for us to find the displacement. It's just going to be the vector from A to B. I'm just writing down A and B here for myself. I'll just double check I don't get it wrong. How did I manage that? I did. Oh, I wrote down the force by accident. Sorry, my bad. So B is 12, 10, 2. Okay, so let's see what the next page has in store for us. The displacement of the force from the fulcrum. So that's going from A to B. So the displacement of the position of the force, basically relative to the fulcrum, is vector from A to B, which is the coordinates of point B minus the coordinates of point A. The coordinates of point B are 12, 10, 2. And the coordinates of A are 2, 2, 6. So 12 minus 2 is 10. 10 minus 2 is 8. 2 minus 6 is minus 4. So now we're going to calculate the torque, which is not force dot displacement or displacement dot force, because it's a vector, not a scalar. So it's a cross product, vector product, and the order is d then f. If you do f then d, you're getting minus the answer. You will lose marks from me. So I'm just going to go back and get the force here. So the force is minus 9, 9, 12. And so what I need to calculate is, maybe I'll just put it in here. So the displacement is 10, 8 minus 4. Cross with the force is minus 9, 9, 12. I probably shouldn't have put them there. This is equal to, now how do you calculate these cross products? With a determinant, I, j, k, the components of d. If you put the components of f, you've calculated f cross product d, which is minus the answer. So components of d, 10, 8, minus 4. Components of f, minus 9, 9, 12. Write down the first two columns again. So that's I, 10. So this weird thing is how we calculate these vector cross products. J, 8, 9. Then we do right down diagonal. So you multiply along the right diagonals. I by 8 by 12. J by minus 4 by minus 9. K by 10 by 9. So the I by 8 by 12 is 96I. J by minus 4 by minus 9. You can multiply the numbers together first. Minus 4 by minus 9 is 36 by J. And then 10 by 9 is 90 by K. That's the right down diagonals. Take away the left down diagonals. J by 10 by 12. I by minus 4 by 9. K by 8 by minus 9. So the first one, 10 by 12 is 120 times J. The second one, 9 by minus 4 is minus 36 times I. And finally, 8 by minus 9 is minus 72 times K. And we'll tidy this up, and this will be our moment vector. Now be careful, you're comparing i's with i's, etc. So, and hopefully I haven't made a mistake. 96i minus 36i is 96i plus 36i, which is 132i. 36j minus 120j is, I think, going to be minus 84j. And 90k minus 72k will be 162k. Now, how about units? So get the units of the force and multiply it by the units of the distance. Works the same way. So let's get the units of the force, newtons and centimeters. Newtons and centimeters. I wouldn't mess around changing this. You could change it to 1.32 I minus 0.84 J plus 1.62 K Newton meters, which would be joules, but look, there's no real need there. Find the magnitude of the torque, because that was the second part of the question. It's just the magnitude of this. So do Pythagoras square root sum of the squares. Remember, careful with a negative, you put it in brackets. And we'll put this into the calculator and we'll round it to 4 significant figures. So what have we got? Square root of 132 squared plus, I'm just putting in 84 because minus 84 squared is the same as plus 84 squared plus 162 squared. And I'm getting 4 significant figures, 225.2. Put in your units, newtons, centimeters. So that's it. There's a few elements here. You have to get that the displacement goes from the pivot to where the force acts. You have to get the order right, that it's displacement cross product with force. You have to know how to calculate the vector cross product. You're putting the first vector in the second row and the second vector in the last row. And then you do this right down diagonals minus left down diagonals business. Yeah. And then the magnitude is Pythagoras. Okay, I think we have one more example, maybe two, we'll see. So the pole in the diagram below is subject to a 60 Newton force that is directed from C to B. So if I put a displacement on this, now that's not the displacement, this is the direction of the force. Okay, now I might call this V, the vector from C to B. That is the direction of the force. The question is determine the magnitude of the moment created by this force about the support. Now here you can see that the displacement of the force is A to B. So where does the force act at B? Where is that relative to the fulcrum? It is the displacement from A to B. Okay, so what we have here is we have the direction of the force and we have the magnitude of the force, which is 60 newtons. And our job is we can calculate the displacement. That's not going to be an issue for us. How do we get the force vector? Well, again, what we should do is we should find a vector of length 1 in the same direction as CB. So that's CB hat. And then the force vector will be 60 times CB hat. That's what we should do. We might get a little bit of a shortcut, but that's basically what we should do. And then the question is find the magnitude of the moment. Now you could, as I said, it doesn't ask you for the moment here, so you could actually find the angle between this force. Actually, I'll just outline it. If you're very clever here, you can actually get away with doing a lot of work. So notice that if the force is in this direction, same direction as C and B, that the angle between the force vector and the angle between the displacement is the same thing. So I'm saying here's displacement and here's force. Now I'm going to put the force over here. It's displacement, force. And if the force, remember, is in the same direction as C to B, and what I'm trying to say here is that the angle theta angle. So let me clear, this is not actually the way I recommend you do it, but it is a shortcut. Just to show you what you could do here. Angle between F and D, same as between CB and D. And you can find this angle theta using the dot product. So you could find the angle using dot product. CB dot product with displacement is equal to magnitude of CB times magnitude of displacement times cos of the angle in between. So you could solve that little equation for theta. You'd have the theta, and then this question is only looking for the magnitude, and the magnitude of the moment is the magnitude of the displacement, which you would already have from here. The magnitude of the force, so that's just 60, that's given in the question. And then you'd have found the angle there, you could take the sine of it. So that would be possibly easier than what we're going to do, but we're going to do it, especially because I could just ask you to find the moment itself. Okay, so there's important things to say. The force is not the vector from C to B. It's the same direction as it, and the force is not 60. That's the magnitude of the force. So this is the direction, essentially, of the force, and 60 is the magnitude of the force. But them on their own do not define the force. So we'll do it as we recommended in the green here. So we'll find the vector from C to B, which is the direction of the force. It is, as before, the coordinates of B minus the coordinates of C. The coordinates of B are surely up in the question, 1, 3, 2. Minus C, which is 3, 4, 0. So you get 1 minus 3, which is minus 2, 3 minus 4, which is minus 1, and 2 minus 0, which is 2. So that's the vector from C to B. It's not the force. In fact, we should draw the force possibly separately altogether here. And the force vector does not have to be in proportion to the displacement vector because they're different units. You can't really compare them in that way. Okay, so it's magnitude of CB because we want to find CB hat. So we'll find CB hat by dividing this by its own length. So the magnitude of CB, we do Pythagoras, square root sum of the squares. So we get minus 2 squared, which is 4, plus minus 1 squared, we're up to 5, plus 2 squared, are we up to 9? 2 squared plus 2 squared is certainly 8 plus, yeah, so that's 9. Square root of 9 is 3. Now at this point, you could notice that you could do this. This is another option. You don't have to go to the unit vector. So you could notice that the force, so the length of C to B is 3 and the length of F is 60. So you could notice that F is 20 times longer or 20 times bigger in magnitude. It is a bit confusing, I accept here what we're doing, but I think it's going to be easier. That's one option. I think it's going to be easier to do this way. So the force is 60 times the unit vector. So we'll find the unit vector from C to B on the next page. Okay. Or we note the shortcut. The shortcut is that the magnitude of F is 60 and the magnitude of C to B is 3. And therefore, because they're in the same direction, if I multiply CB by 20, it becomes length 60. So that's, now we won't do the shortcut. We're going to, we better go back and find CB hat. We'll do that up here. So CB hat is equal to CB divided by its own length. CB is minus 2 minus 1, 2. Its length is 3. And now, so that's length 1 in the right direction for the force, but the magnitude of the force is 60. So I get this little green thing, but the force is 60. That's length 1, the little green length 1. If I want to get the force, I need to multiply that by 60. So I get that the force is equal to 60 times CB hat, which is 60 times this thing. And the 60 divided by 3 gives me 20. And so I end up with 20 by minus 2 is minus 40, 20 by minus 1 is minus 20, and 20 by 2 is 40. And of course, you get the same answer if you do 20 by CB. So the moment we know is equal to, and we'll have to focus on the question in a moment. We'll do that. Like, what is it actually looking for? So we know the force. The displacement is given by AB, it says. So let's go back. Let's look at our picture. Yeah, the displacement goes from A to B. B is coordinates 1, 3, 2. B is 1, 3, 2, and A is the origin. 1, 3, 2. So we have a force up here in the top right corner. We have a displacement, and the cross product of the displacement and the force will give us the moment, and then the question asks us to find the magnitude of the moment, so we'll do that. So let's find the moment. So the moment of this force is displacement cross product with force. How do we find this yoke? We do I, J, K. The components of the displacement, which are 1, 3, 2. And then the components of the force, minus 40, minus 20, 40. I could have made it a bit bigger. Let's see. And then what you do, you write the first two columns again. I1 minus 40, J3 minus 20. And we're going to do right down diagonals, I by 3 by 40, J by 2 by minus 40, K by 1 by minus 20. So that'll give us, say, I by 3 by 40 is 120I. J by 2 by minus 40 is minus 80J. K by 1 by minus 20 is minus 20K. That's our right down diagonals done. How about the left down diagonals? J by 1 by 40, I by 2 by minus 20, and K by 3 by minus 40. So J by 1 by 40 is 40J. I by 2 by minus 20 is minus 40I. And K by 3 by minus 40 is minus 120K. And so we're going to find the torque. So careful to do I's with I's, J's with J's. So 120I minus 40I is 120I plus 40I is 160I. Minus 80J minus 40J is minus 120J. And finally, minus 20K minus 120K is 20K, minus 20K plus 120K, which is 100K. Now we may as well, we're engineers, well, yeah, anyway, put in the units. So we need the unit, this is distance by force, so we need units of distance and force. I think we'll get them on the previous page. Units of meters, and look at the diagram, it's meters and newtons. So if it's meters and newtons, units of force by distance will be Newton meters. Now we have a habit, I can't explain it completely, but we don't, if you're working with work, you can call a Newton meter a joule. But if you're working with a moment, you don't call a Newton meter a joule. I'm not 100% sure of the reasons why, even though I've Googled it about 100 times. The way I think about it is joule is designed for energy. It's definitely kind of associated with a scalar, whereas Newton meter is associated more with a moment, which is a vector. But to be honest, in my head, I think maybe what it is, I think there's some radians around. So you might say, what are you on about radians for? I think there's some kind of thing knocking around. I'm not sure. I probably didn't show this. Say this. Now radians, it doesn't make a big difference because radians, if you go and Google what a radian is, it's a proportion of length, so it's meter over meter, which has no dimensions. But I think that's why it's something to do with it. Or you can Google it. There's no point me Googling it. I keep forgetting it. If something doesn't make sense to me, it doesn't matter how many times I Google it, I can't remember it, and that's something I can't. The end of this question anyway is find the magnitude. So we want to find the magnitude of this thing, do Pythagoras. 160 squared plus minus 120 squared plus 100 squared. And to four significant figures, what are we talking about here? So square root 160 squared plus 120 squared plus 100 squared, I get 223.6. That's four significant figures, Newton meters. Okay.